Welcome everybody to part 3 of this YMFC 3D video session. In this video I'll explain to you what a gyro is and how to get useful data from it. Now, as described in part 1, the gyro that I use is this L3G4200 breakout board from Parallax. Now, I also noted that you could use this L3GD20 breakout board from Adafruit. This gyro is the upgrade to the L3G4200 and should work exactly the same. The only difference is the I2C address of the device. First, it is important to understand what the output of a gyro represents. When we look at the manual of the L3G4200 gyro, ST Microelectronics describes the gyro as a 3-axis angular rate sensor. To visualize this, I made a small program that produces a pulse of 2 divisions wide on the scope. The additional length of the pulse is linearly coupled to the output of the gyro. The length of the pulse changes when the gyro is rotated along the jaw axis. Now, because the gyro only senses rotational motion, its output will not change if I tap on it or shift the gyro without rotating it. As stated in the manual, the gyro output is an angular rate. This means that the output is 0 when the gyro is stationary. With a different angular rate, the length of the pulse will change proportionately. Because we only need to correct the unwanted movements of our multicopter, the gyro is the ideal sensor for our project. Now let's look at the manual again. I'll make a link in the description so you can download it. The gyro uses registers that we can use to set up the gyro and read our angular rate data from. In chapter 6 and 7, the registers are explained. Now the registers that we will use are control register 1, control register 4, and the output of the X, Y and Z axis. Now when the gyro is powered, these default values are loaded in the corresponding registers. If we look at control register 1, you can see that we can set various options. The output data rate and bandwidth are set up correctly by default and will produce good quality angular rate data without much noise. Now here you can see that the gyro is in power down mode by default. To get the gyro to work and read angular rate data from it, we need to put it in normal mode. The X, Y and Z axes are enabled by default, so we don't need to change this. The only thing that we need to change in control register 4 is the BDU bit. Because the angular rate data is transferred by 2 bytes, we need to be sure that the 2 bytes are from the same sample time. By setting the BDU bit, the output register X, Y or Z is not updated while reading the data. After a complete read of both bytes, the register will continuously be updated and always contain the most recent angular rate data. And last but not least, we can read our angular rate data from the X, Y and Z output registers. The angular rate data is a 16-bit value and is divided over 2 registers of 8 bits. To get the complete value, the bits need to be shifted to their correct positions. The I2C communication protocol that we will use for communication with the gyro is described in the manual. The most important parts are the I2C address of the gyro and the fact that you can change it via the SDO pin. Depending on the state of the SDO pin, the address of the L3G4200 is 104 or 105 in decimal notation. On the breakout board from Parallax, a pull-up resistor is connected to the SDO pin, making it the address 105. All the other interesting parts for communicating with the gyro are handled by the wire library that we will use. The wire library comes standard with the Arduino software, so you don't have to download it. So, what do we need to do in our Arduino program to get this gyro up and running. Now first we need to include the wire library. And same as the serial output, we need to start it so we can use the wire library functions. This line starts the communication with the gyro. Because we want to set the bits in register 1, we need to send the address of the register that we want to write to. In this case, 20 in hexadecimal notation. Now that the gyro knows what register we want to write to, we can send the actual data. Now it really does not matter what form of data you send, decimal, hexadecimal or binary, it is all the same. And finally, we can close the communication with the gyro. And we do the same thing for register 4. Here you see the main part that reads the X, Y and Z data from the registers. Again, we start communicating with the gyro and tell it that we want to start reading register address 28 in hexadecimal form or 40 in decimal form. After reading a register, the address needs to increment so we can read multiple registers at once. As said before, this is described in the manual. We need to set the most significant bit of the register address. The most significant bit, as described in the manual, represents a decimal value of 128. By adding 128 to the decimal register address 40, we get a decimal value of 168. After this, we close the communication with the gyro. Now that the gyro knows what data we need, we can request 6 register values from the gyro. Now this can take a while, so we need to wait until all the data is received in the buffer of the processor. After that, we can start reading the register values. Now as said before, we need to combine the two registers to get a complete 16-bit value. As you can see, we have a so-called high byte and a low byte. In this line, the bits of the high byte are shifted 8 positions left and are loaded into the gyro roll variable. After that, the low byte is added to the same gyro roll variable. Now the gyro roll variable holds the complete 16-bit angular rate data of the x-axis. I'll post a link in the description for more information about this subject. And we can do the same for all axes. This is the complete program that you can download. I'll put a link in the description. The part that I added is this calibration part. Most gyros have a little offset that causes the multicopter to drift. Therefore, we take multiple samples, in this case 2000. After this, the sum of the 2000 samples is divided by 2000, so we can get an average of the offset. This offset is subtracted from every measurement and prevents the multicopter for excessive drifting. Another part that I added is the visualization of the angular rate and the corresponding directions. As described in part 2, the standard for our roll, pitch and yaw axis is based upon this aircraft. This means that the gyro output needs to correspond with this image. Now let's upload the program to our multicopter and open the serial monitor. The first thing that you see is the calibration of the gyro. Now don't move the multicopter during this calibration process. And after that, the angular rate values and directions are shown. The right wing up or down, nose up or down, and nose left or right need to correspond with the movement of the multicopter as shown here. If the direction of your gyro don't correspond to the serial output, you can change their direction by multiplying the angular rate by 1 or -1. If your gyro not responding to the program, or you use the L3GD20, it is possible that the gyro's address in the program is incorrect. For this, I wrote a small program that you can download. I'll post a link in the description. This program checks every address of the I2C bus to see if the gyro responds to the Who Am I request. When the gyro responds, it will show the type and address of the gyro on the serial output. In case the gyro does not respond, a failure message will appear. If this happens, you need to check if the gyro is correctly connected to the Arduino Uno. And that brings us to the end of this video. If you have any questions, just post them in the comments section and press like if you find this video useful. So thank you for watching and see you next time.